In this video, I'll cover the very basics of what capacitors are. So capacitors can be formed by placing a couple of conducting plates in front of each other, and they're typically separated by some sort of a distance d. And in the separation space, we put an insulating material or dielectric material. And a dielectric material is just an insulator that allows electric fields to go through them. And each one of the plates typically have some sort of an area. Anyhow, so if we connect these plates to some sort of a battery in here, what happens is there will be some, there's an insulator in here, but because there's a difference in voltage in here, there will be some sort of a charge displacement in here. And the charge displacement, well, pretty much will have some negative effect in here, some positive effect in here, and so forth. There will be a separation of charge, and the separation of charge will create what we call an electric field. So this can get really complicated, but we're not interested in that. What we're interested in is if we disconnect this battery, there's nothing to move the charges back to where they were. So what happens is we have an electric field that is, in ideal world, that is basically just there. And that electric field was formed by providing energy. So what happens now is that capacitor stores energy as an electric field. So the battery is disconnected. If you take these capacitor or these two plates and connect them to a bulb or a light or any other element or resistor, it will release that energy and it will just basically give that energy to that element. So this is why capacitors are storage elements, are energy storage elements, because they store energy as an electric field and they release it. So the details of the separation and whatnot can get really complicated, and we can spend some time on it. But for the purpose of circuit analysis, I'm only interested in their terminal behavior. How do they affect circuit, or how do they affect different circuit variables, such as current and voltage, when we put them in a circuit? So let me just focus on how they are placed in a circuit. So the first thing I'm going to focus on is their symbol. So the circuit symbol for them is like this, which is basically a couple of plates, and it reminds you of the plate. That's where the symbol is coming from. So sometimes you'll see it in two parallel lines, and the reason why is because we have some dielectric material in here will impose some sort of a polarity. So you'll have a negative and a positive, and typically the negative will have a curved line. But for our purposes, for circuit analysis, I'm not interested in practical capacitors. Practical capacitors differ in the size, shape, the dielectric material, and so forth. I'm not interested in any of that. What I'm interested in is just generally how do they affect circuit elements or circuit variables. Okay, so that's the symbol for them. But so how do we measure them, or how do we distinguish between different capacitors? As it turns out to be, that capacitors have what we call capacitance, and a capacitance is usually termed as C, and C is typically computed, or you can compute it depending on the type of capacitor that you use, and the rule for that is just simply epsilon times A divided by D, and A is just the area of the plates, D is the distance between the two plates, and epsilon relates to the dielectric or the insulator material that you put in them, and this is called permittivity. So this is not very interesting. This is if you're building capacitors, this is what you focus on, but for circuit analysis, we're just going to assume that we have a capacitor, and I'll give you what the capacitance is. Okay, so a capacitance usually have some sort of a unit, and the unit for capacitance, or for capacitance, is farads. Okay, but farad is really a large unit, so you will rarely see it in actual circuits. So what you will see is some variation of it, which is microfarad, which is basically 10 to the negative 6 farads, and then also you might see picofarads, or maybe millifarads and whatnot, and pico, I believe it's 10 to the negative 9 or 10. Okay, all right, or actually pico is 10 to the negative 12. So just to make sure, I believe it's 10 to the negative 12. Anyway, so that's a symbol, that's a unit for it. Okay, so, and when we saw it, it basically stores elements and so forth. Okay, so how does it affect, how does current and voltage relate to each other? So if I have a current and voltage, so for example, if I have a voltage in here and I have some sort of a current that is going that way in here, this is, let me just correct that. Okay, so let's assume that I have a current going through that particular capacitor, and we have some sort of a voltage. How do I relate I to V? And as it turns out to be, if you go through Maxwell equations, you'll be able to cover this. But the current and the voltage, and I'll use lower cases in here, because typically lower cases are associated with something that changes, and typically currents and voltages in capacitors and inductors change. But anyway, so I equals typically C times dV divided by dt. And the dV divided by dt is just a derivative of the voltage across it in terms of time. and the C is the capacitance. So this is how the current and the voltage relate to each other. So the voltage and the current relate to each other with this particular equation. Now, one note to make sure that you understand, passive sign convention still applies in here. So in this particular case, you will see that the current is hitting the positive, so you put a positive. But if I drew the current in the opposite direction, you would have said that, well, it hits the negative, so I'll have to use negative. So passive sign convention still applies, similar to what we did with Ohm's law. Okay, more on that. This particular circuit element is still a linear element, and the reason why it's linear is because if I draw dV divided by dt versus I, the relationship between the voltage and the current, still gonna get a line. That's why it's linear, and of course the slope of this line is depending on C, the capacitance. All right, we can go ahead and say, okay, this equation will give me really interesting concepts here, or a couple of very, very important concepts. So let me just cover them. So the first one is typically in DC circuits, in DC, what we have is V is constant. Typically it's a constant, some sort of a value. So the way we deal with constants, well, DC direct current circuits have a voltage that is 5 volts, 10 volts, whatever it is, it's a constant. So if we take this concept and put it in here, the derivative of a constant is typically 0. So that means I is 0. So in cases where we put a capacitors in a DC circuit where the voltages do not change, so the dV divided by dt, it doesn't change with time, so the derivative will be 0, because the derivative of a constant is a 0. That means I will be 0. And as it turns out to be, that if you put a capacitor in a DC circuit, that particular capacitor does not exist. You can deal with it as if it's an open circuit. That's what you can deal with it. And of course, in an open circuit, if you guys remember, I is just simply 0 in that particular case. So in DC circuits, capacitors act as open circuits. So in DC circuit and in circuit analysis in general, capacitors and inductors for that matter, they're more interested when the current or voltages change. All right. So the next thing, well, let's assume that the voltage is actually changing or the current is changing. So let me just take a look at this concept. So let's assume that for some reason the voltage just basically jumped between some sort of a value to another value. Like let's assume it jumped from 0 volt to 10 volts instantaneously with no delay whatsoever. By doing this, what I'm assuming by no delay whatsoever, the voltage, so this dV divided by dt, if you think about it, the voltage jumped from 0 to 5 or 0 to 10 with no delay whatsoever. What I'm telling you is that means t is basically 0. So this particular change actually goes to infinity, because dt it goes to 0 because the change happened in 0 time. So dt happened to 0. That means the whole dv divided by dt, the derivative of dv divided by dt is infinity. That means I is also infinity. And of course, in typical circuits, if I is infinity and I'm computing the power, I times V, that means I have a power that is infinity, which doesn't make any sense. So as it turns out to be, that capacitors oppose the change in voltage. So they don't allow change in voltage or these particular drops that are instantaneous. So there's some sort of a delay that will happen. Okay, and this is very important, and you will see it later in future concepts when we talk about capacitors. You will see that capacitors introduce some sort of delays in voltages. But anyway, so the key takeaways in here is a couple of things. You put a capacitor in a DC circuit, it acts as an open circuit. And if it's not in a DC circuit, it's in a circuit where the voltage is changing, it opposes the change in voltage. It will not allow a drop between 0 to 5 instantaneously. There will be some sort of a delay. Okay, so again, the relationship between the current and the voltage is I is typically C equals dV divided by dt. Of course, I'm not writing these in here. I should probably. This is I in terms of t, and this is V in terms of t. They're both functions of time. And of course, we have passive sign convention in here. Now, sometimes what happens is you have the voltage across the capacitor, and you compute the current using this equation. But in other cases, sometimes we know the current across the capacitor, but we need the voltage. So we need to do a little bit of algebra and just compute what the voltage equation is. So how does the voltage relate to the current versus the current relating to the equation? So we do a little bit of algebra, and I'm assuming for the sake of simplicity, I'm just going to assume the positive cases in here. It's just simple. Later on, you can just basically add the negative sign with passive sign convention. But anyway, if you do a little bit of algebra, and I'll just use I instead of I of t times dt, or let me just keep it, equals C times dV in terms of t. So what we're interested in is this particular V in here. So let's do that here. So what we're interested in is dV in terms of t equals 1 divided by C I t dt. So I'm interested in V. So what I'm going to do is I'm going to do some sort of a integral in here. I'm going to integrate both sides. So by integrating the dV, and let me just basically the dV dt, I'm going to just call it some sort of a dV in terms of x, okay? Or maybe I'll term the whole thing here as d of x. I'll just call it d of x, and of course it will go from some sort of an initial value t0 all the way to t. That's what I'm interested in. The reason why I wrote it in x in here because I wanted to use v of t on one of the integral limits. All right, so what we do is we have 1 divided by c. We also integrate in here, and then what we have is we have I, well, it's a function of time, but because I want to use time in here, t0 and t, so that I don't get confused, I'll just basically say it's a function of tau, and this is here d tau. Basically, I changed the variable t to tau, okay? All right, so we do these integrals in here, and what we get is v of t minus v of t0, okay, equals 1 divided by c, and this is t0 to t, I of tau, times d tau. So that means v of t equals 1 divided by c, t of 0 to t, I of tau, d of tau, plus v of t 0. All right, and this here, let me just highlight it. This here is the equation of how v relates, or v of t relates to I of t. So let me just talk a little bit about it so that we understand what this v of t is. This v of t is initial voltage. So sometimes I'm going to give you a capacitor. It's not necessarily that initially the voltage across it is 0. If it is charged and it has some sort of an energy stored in it, it will have some sort of voltage, and that's what we call an initial voltage. And we'll see this equation helpful later when we deal with circuits that contain some sort of switches, and I'll tell you, well, it has a voltage, and then I close the switch and whatnot. For today, I'm not going to cover this, or for this video, I'm not going to cover this. We're going to cover it later. But for now, what I want you to understand is the following. What we have is we have some sort of an initial voltage on the capacitors. Sometimes we consider that 0, that's it. T0 doesn't have to be at 0. Sometimes we do changes throughout time. So sometimes T0, the initial time is 0. Sometimes it's 1. Sometimes it's 2 because I'm doing things throughout. So at T0, the initial time, that will be the voltage across it. So the other thing that I want to pay attention to, a passive sign convention, you will put it in here. So you will have passive sign convention. So remember, I started by saying let's focus on the positive. If I didn't, I would have ended up with a positive negative in here. That's what would happen. Similarly, you will see that there will be another sign in here that you might get positive or negative in here, depending on whether this initial voltage across the capacitor is the same in here. That will become a lot better or a lot more explained when we solve the exercises, and we'll see it. But just pay attention to the fact that I might have positive and negative in here and positive and negative in here. This comes from passive sign convention. This comes from whether the initial voltage is in the same voltage that I'm looking for. Anyway, for now, just remember this. That's what you need to remember, or you need to understand this. All right, so moving on, what we can do as well, we can compute the power. So now we have the equation for the current in terms of voltage, the equation for the voltage in terms of the current. Okay, now what we can do is we can do some similar analysis to compute what the power is. So you probably know by now the power of any element is typically I times V, and of course passive sign convention, you have to put positive or negative. For now, we're just going to focus on the positive as I'm usually doing. So we have that. So it's simply, you can just compute the I and the V, but what we can do is we can just basically take this equation and put it in here. So I know what the I is. So I is just simply equals, let me just do this here. I is C times dV divided by dt, and that's basically times V. So you can compute the power this way. This is one equation to compute the power. Okay, another equation to compute the power is, instead of substituting the I by the value that we have in here, we can substitute the V in here and just put it. And again, the power and all of these are functions of time. So P of t, I of t, and V of t. I'm just not writing them, and capacitors are more interested when things are changing with time, not necessarily in DC. All right, so we can also compute the power as P equals just simply, we keep the I, and what we do is we replace the V with 1 divided by C. And here, actually, let me just do it this way. This is simpler. 1 divided by C from T0 all the way to T, I of tau, D of tau, plus V of T0. Okay? You can just compute it this way. And again, passive sign convention applies in here if you wanted to. This is passive sign convention. All right. Lastly, what we can do is, since we're talking about energy storage, we can technically compute the energy stored in a capacitors. And the way we compute energy is by using this equation. So power is typically the change of energy throughout time. that means the energy, dW, or the work that you do, okay, energy or work, okay, is just simply P times dt. So if you're interested in just energy, what we can do is we can substitute this here, P, which is just simply C times, we can do, well, let me just think about it here. So we have P, and it's basically C times dV times dt. So let me just use it in here. All right, so I'll take this rule in here and just basically substitute what the P is, and that's C times dV divided by dt times V times dt. And of course, this dt goes with this dt, so that tells me it's C times V times dV. That's basically dW. So if I take the integral of both sides in here, okay, and this, of course, I'm going to do this from 0 to W, so I'll change the variable for this guy in here, and I'll make it into X. Okay, and this one here is similarly, I'm just going to change the V's to Y's, okay, so that I can go from 0 all the way to V in here. So that tells me that it's W is just simply C, and that here is typically y squared divided by 2 from 0 to V, and what we can do is W, which is the amount of energy, is just half of C times V squared. So this is how you compute the energy across some sort of a capacitor. So what you do is a half of C of V squared.